In question 1, we know that the amount of money spent on food per week by a family has a mean of 150 and a standard deviation of 25. We don't know the exact distribution it follows, but we know the mean and the standard deviation. And then suppose we take a random sample of 81 families and we calculate their sample mean food expenditures. So we take our sample of 81 and calculate the average food expenditure in that sample. What's the distribution of the sample mean? Well, we don't know the distribution of the population. We don't know if it's normal or anything. But since we have a sample mean, we can see if we can apply the central limit theorem. To see if we can apply the central limit theorem, we have to check if two conditions are satisfied. One, do we have a large sample? When we say large, typically the rule of thumb is we check if the sample size is larger than 30. Then we check, do we have a random sample? So is our sample random and independent? So let's check if those are true. Well, first let's check our sample size. Our sample size is 81 families, and well, 81 is greater than 30, so this condition is satisfied. Then we check, do we have a random sample? Well, it tells us that we do. So we know that our sample is random and we can assume that it's independent. So this is true. So now we can apply the central limit theorem. And well, what is the central limit theorem? It says that for a large random sample, we know that the distribution of the sample mean, I denote the sample mean with this notation here, x bar, it's distributed approximately, normally, with mean equal to the population mean, and standard deviation equal to the population standard deviation divided by the square root of the sample size. So this tilde means distributed. The dot above here means approximately. This x bar here is the sample mean. The n here means normal. The mu here means population mean. Sigma here is the population standard deviation. And n here is the sample size. So this is quite a powerful theorem, remember, because regardless of how the population is distributed, if we have a large enough and random sample, we will always know the distribution of the sample mean. So now let's fill this in. So let's listen to the actual numbers. So we know that the sample mean is distributed normally. Well, so what's the population mean? The population mean we're given is 150. And what's our population standard deviation? It's 25. And what's our sample size? It's 81. So the square root of the sample size is the square root of 81, which is 9. So here we have completely described the sampling distribution of the sample mean. Next, let's find the probability that the sample mean is no greater than 160. So putting that into notation, let's translate that into a probability statement. So we want the probability that the sample mean, x bar, does not exceed 160. So no more than 160 is less than or equal to 160. Now, how do we calculate this? Well, I know that my sample mean is normally distributed, so for any normally distributed variable, to calculate probabilities associated with it, all we have to do is convert it to a standard normal. Remember that our conversion formula for any normal variable is we take the variable divided by its mean and divide by its standard. Subtract its mean and divide it by its standard deviation. So this is equal to the probability that our standard normal is less than or equal to 160 minus the mean. Remember, the sample mean is distributed normally with mean 150 and divided by its standard deviation. Careful here that the standard deviation of the sample mean is not 25, it's 25 over 9. So divide by 25 over 9. If you plug that into your calculator, this equals the probability that z is less than or equal to 3.6. I can look that up in my table. I notice that it's a very large z-value, so it's not exactly in my table, so I can approximate the area to the left of it with 1. So there's a 100% chance that the sample mean doesn't exceed $160. Let's move to part C. Part C, we want to find the probability that the sample mean is exactly equal to 150. So we know, as a reminder, the sample mean is approximately normally distributed with mean 150 and standard deviation 25 over 9. The normal distribution is a continuous distribution. What does it mean to be a continuous random variable or to have a continuous distribution? That means this is true of any continuous random variable. It means our sample mean can take an infinite number of possible values. That's part of the definition for a continuous random variable. So if our sample mean can take on an infinite number of possible values, then the probability that it takes on exactly any single value is 0. Because a 1 out of infinity is really, really infinitesimal, or 0. So this is a fact for any continuous random variable. The probability that any continuous random variable equals any single value is 0. Part D. Let's say one family is selected at random. What's the probability that the family will spend at least $160? Now here's where you need to be careful. Whenever you're working with these kinds of problems, you need to pay attention if it's asking about a single observation, a single family, a single individual, versus when it's asking about the sample mean. So here we're asking, what's the probability that any single family will spend at least $160? So remember that single observations follow the population distribution. Whereas the sample mean, or sample means, follow the sampling distribution. When I talk about the sampling distribution, That's the one that we arrived at using the central limit theorem. This right here is our sampling distribution. So we know that the family belongs to the population distribution. As a reminder, what's the population distribution? Let's scroll up and see. So we were told that the population distribution has a mean of 150 and a standard deviation of 25. We don't know if it's normal or not. Now, to calculate this probability, what we'll do is we have to assume that the population distribution is normal. In other words, that x, notice I'm not saying x bar, x, just a single observation, is normally distributed with mean 150 and standard deviation 25. Here, when I talk about x, I'm just talking about a family's expenditures. So then we want to calculate the probability that x is at least 160. So the probability that x is greater than or equal to 160, which is equal to 1 minus the probability that x is less than 160. Remember that I'm converting this to an area to the left because our normal table is only in terms of areas to the left. So now I want to convert this to a standard normal. So I take 160 minus 150 divided by the standard deviation of the population distribution, which is 25. If I plug this into my calculator, my z-score will be 0.4. If I look this up in my z-table, the area to the left of 0.4 is 0.6554. 1 minus 0.6554 is 0.3446. So the probability that any single family will spend at least $160 is about 34.46%. Part E asks, for answering these questions, parts B, C, and D, did I have to make any assumptions about the population distribution? Explain why or why not. So as a reminder, in parts B and C, we were looking for the probabilities associated with the sample mean. I'll highlight this. The sample mean. And part C, we're asking about the probability that the sample mean is at least 150. So in parts B and C, we were using the central limit theorem. So we did not have to make any assumptions about the population distribution. We didn't need to know anything about the population distribution, whether it was normal or not. Population distribution, because we used the central limit theorem, I'm going to abbreviate it with CLT, to derive the sampling distribution. We were given the mean and the standard deviation of the population. Those were 150 and 25. And then we just used the central limit theorem to find that the sampling distribution was normal with mean 150 and standard deviation 25 over 9. So for parts B and C, no assumptions about the population distribution necessary. Whereas in part D, we were dealing with a single family. And so therefore we had to use the population distribution And well, to calculate the probability that a family spends at least 160, we had to assume that the population distribution was normal. So part D, yes, we had to assume the population distribution was normal because we were not given this information initially. Because remember, originally in the problem, it didn't tell us that the population distribution was normal. It just gave us the mean and standard deviation. So to calculate this probability, we had to make an assumption that it was normal. Part F. How would we interpret the results if the sample mean food expenditure was $80? Do we have enough evidence to conclude that the population mean is not equal to 150? Well, so let's suppose that the sample mean food expenditure is $80. So let's see what percentile $80 is at. Often when we want to see if a value is unusual, we'll compare it to the rest of the distribution. We'll see at what percentile it is. So remember, the percentile just tells you what percentage of observations are below it. So what percentage of observations are less than 80? Remember that we know the sample mean was normally distributed with mean 150 and standard deviation 25/9. So we can convert 80 to a standard normal. So this is 80 minus 150 divided by 25/9. If I plug this into my calculator, this z-score is very small. It's negative 25.2. This z-score is so small, it's not even on my z-table. But I know that for very, very negative, very small values of z, we can approximate the area to the left with 0. So that tells us that nobody spends less than $80 on average. On average, the sample mean cannot be less than $80. So that tells us, because this is a very tiny percentile value, $80 must be a very unusual, very, very, very unusual sample mean. So in other words, if the population mean were $150, it would be impossible, probability 0, to observe a sample mean as or more extreme in the negative direction than $80. So that probably means that the population mean would not be $150 in this case. In fact, it's probably lower than that. Part G. How would we interpret the results if a randomly selected family spent $80 for food? do we have enough evidence to conclude that the population mean is not equal to 150? Okay, so you might ask, what's the difference between part F and part G? It's kind of a subtle difference. Part F, we're asking, is a sample mean of $80 unusual? In part G, we're asking, is a single observation of $80 in the population distribution unusual? So part F is $80 unusual relative to the sampling distribution. Part G is $80 unusual relative to the population distribution. I know that there's this distinction because in part F we're talking about the sample mean. So the average food expenditure among a sample of families, whereas in part G we're talking about a single randomly selected family. So not a sample. So as a reminder, we assume that the population distribution is normal with mean 150, standard deviation 25. So we want to figure out what percentile is 80 at relative to the population distribution. So I convert this to a standard normal. So I do 80 minus 150 divided by the population standard deviation, which is 25. If I plug this into my calculator, I should get negative 2.8 for my z-score. I can look this up in my table, and I should get that this equals 0.0026. So about 0.2%. So only 0.2% of families spend less than $80. So this is still quite unusual, but unlike part F, not impossible. So it's not impossible that a family will spend less than $80. A single family will spend less than $80. Since it's not impossible, this single family could be an outlier. So we still need more evidence. In other words, we don't have quite enough evidence right now to conclude that the sample mean, or to conclude that the population mean isn't $150.